Alright guys, welcome back. Let's do a little bit more weird chemistry math. We are going to go through quiz 13M. This is the quiz, an example of the quiz that we will be taking on the 18th of March, which is tomorrow. So hopefully you guys get a chance to watch this and take a look at it. If not, you can review this and look at it for the exam, because I'm sure we'll see some of this stuff on there. So just as a reminder, this chapter deals with weak acids and strong base reactions, or strong acid weak base reactions. An important part to remember with this is that we are dealing with not just equivalence points, but we're also dealing with half equivalence points in these reactions, and the pH of the solution at the equivalence point is not going to equal 7 like it does with strong acids and strong bases. So let's jump right in to this first problem and take a look and see what we've got. So it gives us a concentration or a volume of a monoprotic weak base titrated against nitric acid, which is a strong acid, and it gives us the volume and concentration of that. Okay. We've got a Ka value, and we need the molar concentration of NZ. I'm going to have to turn this a little bit so I can write. Okay. Of NaZ. Now, this is basically, we're just running our numbers from the dilution for this. So let's take a look at our formula. So we've got the molarity of our acid times the volume of our acid, and that we're going to set that equal to the molarity of our base times the volume of our base. Now, one quick thing to note here, if you are dealing with an acid and a base that do not have a 1-to-1 ratio, this is a really easy fix at this stage, because you would just write your stoichiometric coefficients on the bottom of those fractions, rearrange it accordingly. Now, these do have a 1-to-1 ratio, so we don't really have to worry about these stoichiometric coefficients at this point. So let's rearrange this to find the molarity of our base. Okay, and then we're going to have, there we go. And then let's plug in some numbers. And then we put that into the calculator, and we get a molarity of 0.02562. Okay, so this is the molarity of our base. Okay, now what is the pH of the solution before the addition of any base, so of any of the acid? Okay. Now, we are going to need our Kb value here. So we have our Ka, and we're going to need to find our Kb. So Kb is going to equal Kw divided by Ka. And when we run that number out, we are going to get 3.7 times 10 to the negative 8. Now, let's write out our reaction here just so that we know what we're looking for. NaZ plus H2O. And when that dissociates here, we're going to get Hz plus OH negative. All right. Now, we're going to take our Kb and we're going to plug in our constants here, or our values. Kb, and that's going to equal to Hc OH negative over NaC. Okay, and these are going to be equal because it dissociates equally. So we're just going to sub this in for x squared, and then we're going to put our concentration that we found in step 1 here on the bottom of this fraction. So and then set that equal to KB. We're going to solve for x. So x is going to be equal to the square root of 3.7 times 10 to the negative 8 times 0.02562. And that is going to give us an x value of 3.079 times 10 to the negative fifth. And now remember that this is our hydroxide concentration. So if we take the negative log of our hydroxide, that's going to give us our POH. And when we run those numbers, we're going to get a POH is going to equal 4.512. And then we take 14 minus our POH to give us our pH, and that gives us a pH of 9.49. All right, so we have our pH before we have added any of our acid. Now, the next part, what is the pH of the solution at the half equivalence point? Well, the beauty of the half equivalence point with these reactions is that at the half equivalence point, your pH is equal to your pKa. And we have our Ka here, so then we just find our pKa, and that is our pH. Okay, so negative log of 2.7 times 10 to the negative 7 is going to be 6.569, which we are going to round to 6.57. There we go. Now, what is the half equivalence point volume of the titration? Now, let's take a look at our original problem again. So, we have 35 milliliters of our weak base, but that's not what we're looking for. We want to know what it was titrated with exactly. So it's titrated to equivalence point with 21.56 milliliter. And so we're going to multiply that by 1/2 to get our half equivalence point volume, which is going to be 10.78 milliliters. And then the last and final question on this, what is the pH of the solution at the equivalence point? Now, for this one, we do have to do the dilution fraction. So we're going to take our original molarity here. If I can actually write 0.02562. There we go. And we are going to multiply that by our dilution fraction. So we have 35 milliliters of our base, and then we are dividing that by the total volume of the titration, which is 35 milliliters plus 21.56 milliliters. Okay, and then when you run those numbers into the calculator, you're going to get 0.01585 molar. Now, we are not done yet. We have got to put this concentration into our Ka to find our value of our pH. So, Ka is going to equal, remember, this is H plus and A minus over HA, right? And our problem gives us our Ka value as 2.7 times 10 to the negative 7. Now these are equal at this point, okay, because it dissociates equally, so we're just going to make those x squared. We're going to plug in our concentration here. And then we are going to solve for x. Okay, this is going to give us an X value of 6.54 times 10 to the negative fifth. And we're going to remember that that is our hydroxide ion concentration. And we're going to take the negative log of that in order to get a pH of 4.18, which makes sense because we have a weak base and a strong acid, so that tells us that our pH at our equivalence point is going to be more acidic. Let me know if you guys have any questions. You can drop it in the comments, send me a text or an email. Again, this was quiz 13M, and this is what we're going to be working on tomorrow in class. Good luck.